So now I would like to write down two fundamental theorems about Laplace transform. So first of all, I would like to give a definition of functions of exponential order. So So we say a function, either real valued or complex valued, defined on the positive time axis is of exponential order if there exists a real sigma 0 and a positive number m, such that the f value of f(t) is upper bounded by n times such an exponential function, for all t greater than 0. Okay. And in this case, f of t is denoted as big O of E sigma 0 t. Okay. So it's called exponential order because it's big O. All right. So now theorem. So the existence theorem. Maybe I think it's pretty right. Your EM. If f of t is defined and piecewise continuous, the positive interval. Okay, so f of t is defined and piecewise continuous on 0 and infinity. And it's of exponential order. Okay. And E. then f of x equal to Laplace transform of K exists for all well-defined for all real part of x greater than sigma 0. So this is called the existence theorem of Laplace transform. Maybe I have write it down. Okay. So if f of t is defined and piecewise continuous on the positive axis, sorry, from 0 to infinity, and is of exponential order, and it's of exponential order, then f of x, right, the Laplace transform of f of t is well defined for all x, its real part is greater than sigma 0. Proof which is equal to okay, and so we take the absolute value this is less than equal to dt. Okay? So the absolute value of this improper integral is less than equal to the integral of the absolute value of the integral. Okay? This is always true. Okay, and so this is equal to e minus the real part of x t. Okay. Or I just write down sigma p square. Sigma is equal to root power s. Okay. Because the imaginary part has an absolute value of 1. Things okay. Right. In case you don't know how to calculate the absolute value. Actually, the absolute value of a phasor is equal to 1 because it's here. Okay, so the absolute value of e to the minus st, this exponential function is equal to e to the sigma minus sigma t. Alright, now we know f of t is of exponential order, so f of t satisfies this one. So we know this one equal to okay, right? So that because f of t, the absolute value of t is less than or equal to this term, and so we have okay. So that it's finite if and only if sigma minus sigma 0 equal to 0. Okay? This is the only condition. Because if this one is equal to 0 or equal to negative number, then the exponential either constant or exponentially grows to infinity. So the integral by explosion. Okay? So this is not finite. So this is finite, means that the integral exists if and only if sigma minus sigma 0 equal to 0. Okay? It's upper bound. Alright? So that's f of x exists if sigma equal to the real part of x is greater than sigma 0 and real time. So the Laplace transform exists for exponential for any function of exponential order. Okay. So note the ROC of f t of okay. So the ROC of a function which is of exponential order contains the set such that the real part of S is the sigma c, but may be bigger. Okay, you have to know that the ROC contains it, and maybe bigger. Okay, maybe bigger. Right. So the theorem, the existence theorem, just tells you that in this half plane, the integral converge all exists. Okay. Any questions? Any questions? The uniqueness theorem of Laplace transform. Okay, two functions f of x and g of f of t and g of t equal to 0 and the same Laplace transform the same ROC, okay, if and only if and only if the set such that f of t not equal to g of t, okay, that's zero length. Okay, so this shows the uniqueness. The two functions, if they have the same Laplace transform with the same ROC, and the only condition is that the difference, their difference is zero length. Okay. So then, if both f of t and the g of t are continuous on 0 infinity, then the Laplace transform of ft equal to Laplace transform of g of t with the same ROC, if and only if f of t equal to g of t for all t. Because they are continuous. So if they are different at certain time point, then you can find a very small open set such that both are different. These two are different. And so the length is not zero. It's not zero. Any questions? Okay. Okay, let me state a lemma before state the main theorem about Laplace transform with derivatives and integrals. Okay, so in a very simple lemma, so if we have a time function over t, the time function has piecewise continuous derivative, so the derivative exists, and the derivative is piecewise continuous. Also, the derivative is of exponential order, so from t is less than equal to m times e to the sigma 0 t. Okay, for some real number sigma 0 and some plastic number m. Then the ft itself is continuous, okay, and also of exponential order. Okay, from here. And the proof is simple. We recall the fundamental theorem of calculus. We can write ft as okay, so we can write down ft by using the derivative of ft. So I have to use half. Okay, sorry. Here. Alright, so this is from the fundamental theorem of calculus. So we have, and so that ft is continuous. Of course, because it can be expressed by an integral, so of course it is continuous. Okay? Now, the x value of ft, okay, is less than or equal to f of 0 plus that okay, we will take the x value. Okay, and so this is f of 0 plus that okay, I have to, sorry. It's m prime. Okay, so f0, and so here, okay, less than or equal to m. Okay, so I apply this inequality. And this is f0, and plus, yeah, I think f0, and here is sigma 0m e sigma 0t. All right, so this is plus m minus 1. P and 1. Okay? So it is m prime the sum prime. Okay? So we can set m prime to be the maximum of this value or this value. Okay. And so we have alpha on this side. Any questions? Because when sigma equal to, when t equal to 0, then this is 0. So this is 1, right? So when t is 0, this is 1. But m is the maximum. So of course, m prime is greater than equal to this number. Okay, and when t is bigger, then we know that well, I think this is enough. So. Okay. Maybe I write a I think that's enough. Because we can always find an epsilon satisfy this condition. Okay, so now the first theorem is about the Laplace transform. Okay, so if f of t is continuous, if f of t is piecewise continuous derivative f t and so suppose f of t has a piecewise continuous derivative, and f of t itself is of exponential order. Then the Laplace transform of f of t is equal to s Laplace transform f of t minus f of 0. Okay. And if f prime t, and if f of t is piecewise continuous, second derivative f double prime t for all t greater than 0, and the first derivative of f t is of exponential order. Then the Laplace transform of f is equal to s squared of Laplace transform of f of t minus x f prime 0 minus x times x f here and minus f prime 0. Any questions about the statement? Right? So you can see the first one. We know f of t has a piecewise continuous derivative. So now, you pick up a sequence of points starting from t0. So t0 is equal to 0, t1, t2, etc., such as t1 goes to infinity and as n goes to infinity. And the first derivative of f of t is continuous on each person because it's piecewise continuous. So this is just the meaning of piecewise continuity. Okay? So now, to find the integral. So because we need to treat the improper integral from 0 to infinity, but we can treat it as piecewise. Okay, so in each finite interval, we can compute the integral. And it turns out that this is equal to the fundamental theorem of calculus plus, okay, by using the integration by parts, right? So this is the integration by parts. Okay, so from integration by parts. Okay, so this is we know the integration by parts. Any questions about the integration by parts? Good. Now, so for Tn, right? So from 0 to Tn, it's equal to right. So the integral comes to sum of several integrals, and so we put the result here. So this is the e to minus st I f t I minus e minus 2 e to the minus x t I minus 1 f t I minus 1 plus the sum of and f of t, right? And you can see that you can cancel, right? This is alternating sum. So so you have minus f0. Okay, when t0 is equal to 0, right? So you have t0 plus s n dt. Okay. So the Laplace transform of the first derivative, which is equal to n goes to infinity of Tn 0. Okay. So as Tn goes to, n goes to infinity, the p sub n goes to infinity, right? Because we pick up the point, the sequence of point in this way. Okay, so now, so this one, so you can see that this is go to limit and goes to infinity e minus xtn of tn. Okay, minus f0. Okay. Plus x limit and go up s times the limit and goes to infinity and 0 dt. Okay. Now when okay, so when the real part of x greater than sigma 0, then we know because f of t is of this order, we have limit convergence exists. Okay, and exists. And in this case, and the limit n goes to infinity, Fdn, okay, the f value, okay, will be less than equal to the limit exponential sigma Tn, and okay, so because that the real part this is sigma, right? The real part sigma is greater than sigma 0. Okay, so that this is go to 0, of course, because sigma is greater than sigma 0. Yeah, so as n goes to infinity, Tn goes to infinity. So this is 0. So we know this is 0. And this one converge. Which shows that the Laplace transform of f prime t is equal to Laplace transform s times the Laplace transform of t minus f of t. And there are all three of prime t contains. There are all three of t. Okay. Okay, so we proved the first part. For the second part, I think that's quite easy. Now, the second derivative of f of t can be regarded as, since the second derivative of f of t can be regarded as the derivative of the first derivative from t. Right? So the second derivative okay, so the second derivative f double prime of t of f of t can be regarded as the derivative of the first derivative f prime of f of t. So we can apply the previous result twice, right? How can we say that? Okay, so this is equal to the Laplace transform of f prime t epsilon. Okay. So this is S, the Laplace transform of epsilon t. All right, minus epsilon 0, right? Is that okay? Second derivative is the derivative of the first derivative, right? So the second derivative is just the derivative of this function. So by previous result, it is the x times the Laplace transform of this function and minus the function that becomes 0. But epsilon t, this is x Laplace transform of f of t minus f of 0 minus epsilon 0. Okay. So finally, we have s prime Laplace transform of f of t minus s of f of 0 minus epsilon 0. And write down. Okay? Okay, I have to stop here. Yes? Midterm examination next Tuesday. Yeah. The range to chapters 1 and 2, 3, 4, and 6. 5 chapters. Yeah. I will finish chapter 6 this week. Okay? And next Monday, we will have quiz examination, number 6. Yeah. It is for chapter 6. Other questions? And the next Thursday, because I will go to United States for a conference, so there is no class. Next Thursday. And then no quiz next Monday. Okay. So November 7th, no quiz. Right? Okay. Right, so see you on Thursday.